This
Fowler.
conference will now be recorded.
I'd like to present myself. My name is Mark Fowler. I'm responsible for Untitled Chapter for the UK, the Middle East, and Africa. My colleague, Dr. Ami Daman, is our Knowledge Center Manager and is the technical backbone of our company. So I'm very happy he's here with us. I would like to split this presentation into two parts. I will just do a quick few slides about who we are and what the company is. And Dr. Ami will take over and present to you the technical portion of the presentation. Okay. All right. Next slide.
Here we go.
Perfect. Eidolon Cedra are basically an embedded track system for all applications of rail. We don't work with ballasted systems. We provide solutions for light rail, metro, heavy rail, industry, crane, anything where an embedded rail system or embedded track system is required. Slide 3. Our ballastless systems have been in the market since the early 70s. We've been recognized from different international rail authorities who have applied our materials and applied them for the last 50 years. Many cases where we've had track installations in excess of 30 years. Our solutions are based around the dynamics of electrical isolation, noise and vibration control, especially in short installation times, and something which plays upon many asset engineers' minds, maintenance. So there's very, very little maintenance required. Due to the environment that's now become a major part of most industries now, we have also moved towards sustainable materials, investing in green technologies, using recycled materials. Some of our key elements within the company, we provide system designs, testing. We have our own engineering department, which is located in Madrid. So as an international company, we try to locate our competence centers in different parts of Europe. We also supply construction support, where we will issue supervisors to provide training, on-site training of installation, and often in cases we will also provide the actual installation. We associate ourselves with the asset managers and asset engineers to try and advise them on how to keep their track maintenance free. And indeed, also when we are talking with track owners, we try to provide competent consultation and supervision form of level. This is our system design center in Haarlem, the Netherlands, where we test all our embedded rail systems for different properties. So we put them through a cycle of 1.5 to 3 million cycles at 4 Hertz to prove the durability of our systems. Obviously, the compliance to EN norms is key for us to succeed. So therefore, we do comply to all the norms, as you can see here. And it's the top one, obviously, being in our industry, one of the main norms to work with. In the UK, we try to keep our supply chain as short as possible. So instead of working through the European outlets as we would normally do, we have a certified supply chain within the UK. Our slabs, as you can see here, are actually manufactured in Cornwall. I know it's the other end of the UK, but it really supplies a good quality product for us. Our cork-elast and chemical materials come from our own factory in the Netherlands. And part of our scope is the engineering and consultation area, where excuse me, it's not COVID, it's just probably not talking too much. We design our own BIM drawings and for our systems. We also do the design works for different types of slabs. So everything that has a design element to it is provided by our application engineering division. Through the construction and support, as you see here on the left in the picture is New Haven from Network Rail. This is a 24-meter double track where we took out the old track and replaced it with slabs and embedded rail system. One of the reasons for here was the existing track system was insufficient, and it was being renewed, I think, every 3 to 4 years. And now with the concrete element and the embedded rail system, we have now set a new standard here at this level crossing, where we expect the level crossing to last up to 20 years. The cork-elast material, as you can see, the cork-elast material was is handballed into the channels. We advise how to do it, the different procedures of pouring the cork-elast, and what you need to do around the installation. And here you can see a close-up of a finished result of a level crossing with embedded rail system. The level crossing system itself is called an LCS 350. Now the 350 depicts the height of the concrete crossing, and it is designed to withstand all the standards of road traffic. Okay, at this point, ladies and gentlemen, I shall hand you over to my colleague, and he will be able to talk through the next slides. Thank you.
Thank you, Mark, for the introduction and a brief overview. And ladies and gentlemen, thank you for the invitation for this very nice event. Unfortunately, it's not real life, but we are online, and I hope in this 45 minutes you get a nice impression of the Eidolon embedded rail system applied in level crossings. The technical presentation will pay attention to the two systems that Mark just finished with. On one side, we have the rail fastening system, which is the embedded rail system based on cork-elast. And on the other hand, we will pay attention to the level crossing slab, a concrete solid element, which is very robust and serve to let both the rail and road crossing traffic pass. A brief personal introduction. My name is Ami de Man. I work for Eidolon since almost 20 years at the Knowledge Center. It's a technical function that I have. I've studied railway engineering in the Netherlands, and I'm active in this field for more than 25 years now. This helps you, so you can also ask very technical questions at the end of this presentation. Maybe embedded rail is not so common in your real life, and therefore I would like to start with a small introduction of the system embedded rail, followed by the way to build embedded rail, the installation procedure, and give you an overview of applications of embedded rail systems. After that, we will pay more attention to the level crossing system. But first, embedded rail. Embedded rail is a rail fastening system that does not use clips, bolts, screws, base plates, etc. All the things you know. No, it's a system based on adhesive anchoring or fixation of the rail in a channel, as you can see in the left-hand picture. The gray material, the dark gray material, is the adhesive, keeping the rail in position. This is a polyurethane material, 2 components mixed and poured in a channel. This stabilizes the rail very well. It's durable, watertight, and it takes care of the transfer of forces from the rail to the supporting structure. Embedded rail is a special type of track form. And in fact, core-class embedded rail, the one which is based on adhesive fixation, is located in a technical niche of all track forms that you may know. The track form embedded rail is in the very right-hand bottom corner, while most systems are used in open track structures. This overview is based on the European standard for testing rail fastening systems, in which discrete supports and continuous supports are discriminated. In discrete supports, we know sleeper supports, booted sleepers, base plates, and etc. that you will see in ballasted and non-ballasted track systems. The specific track form is the so-called packed system, a continuous support, but discretely clipped by means of clips every, let's say, 60, 70 centimeters. It's a continuous support with discrete fixations. They all have in common that the rail is open and accessible, so by definitions they have an open track structure. Other track forms are designed or installed in pavements, so they are covered. Quite a deal of rail fastening systems are basically discrete supports, but just covered by the pavement. So they function as a normal open track system, but they are made accessible by road traffic by just paving the system in. That's an embedded system, for sure, but in essence, the rail fastening system is a one for open track. The third row, however, shows that there are also some track forms that are based on continuous support in a pavement, in which the pavement is part of the track. Examples of these are, for instance, jacketed rails with rubber scrap elements, and they are paved in with liquid concrete that hardens. This gives you a continuous support integrated in a pavement, and it's called an embedded rail system based on mechanical fixation. This system has some advantages, but also some disadvantages, and there our embedded rail system based on an adhesive, the core-glass material, is very different. The construction method of this system starts with first the construction of a channel. So that's the first step. And in this channel, can be made of steel, of concrete, or a combination of these two, the rail is later fixed by means of the adhesive. So this is to give you an impression where embedded rail with core-glass is located within the whole scope of track forms. This second table that I would like to show you is taken from the 2 relevant European standards for rail fastenings. Maybe you are familiar with this, maybe not, but a small explanation from my side may help you to, for instance, to refer this in case you want to specify a rail fastening system for your own track system. Fastening categories range from A+ till E, and in the typical field of application you see for which type of rail traffic they are meant, with the corresponding axle loads, maximum axle loads, typical minimum curve rates, and absolute minimum curve rates. For some of these fastening categories, or traffic modes, there is also a maximum speed indicated. In the last two columns, you may recognize two rail fastenings, embedded rail fastening systems. One with a vignole rail, which is further specified in the EN standard for slab track fastening systems, 13481 part 5. And the other one with grooved rail, more for paved in or embedded track solutions, specified in the EN standard 17319. It's relatively new. It is issued this year and very helpful for light rail and tram companies. Embedded rail that we tested with our test machines and complies with these standards is available in all those categories where you see the crosses. Well, we collect that technical information of our embedded rail systems in so-called system information sheets. And as you may know, we make use of a couple of different products to provide system properties. First of all, the stiffness and the elasticity takes care of a lateral and vertical support of the rail. But by changing and exchanging types of cork and types of resilient materials, we can provide stiffnesses down to 4 millimeters rail deflection, which is significant and helps us to achieve noise and vibration reduction objectives. Very important in inner cities or, for instance, in tunnels going across city centers, going under city centers, sorry. For this, we make use of trackless resilience rail strips, filler blocks, and cork-loss pouring material. This pouring material will isolate the rail from supporting layers and gives a watertight sealing. At the same time, this watertight seal means that there, without ingress of water and all kinds of polluting elements like salt, rust will not occur, and it gives a long service life of the rail itself and the embedding materials. As you may see, this system is not just a simple system. It is based on gluing a rail in a channel, and that means that it is a specialized installation as well as a specialized renewal method that you need to apply. Although it's not a new system, this system has been developed in the 1970s, so almost 50 years live at the moment. A few advantages: minimum number of parts, the rail, the cork-loss material, some filler elements, and resilient strip, makes it durable. The system itself is not much higher than the rail, which makes it very suitable for integration in structures with a height restriction. At the same time, the cork-loss material, a polyurethane, so a synthetic material, is very electrical insulating. That means the stray currents or the currents that go through the rail because of the power system that is necessary for the propulsion of the rail vehicles does not leave the rail, and that is a very good property of embedded rail. Moreover, there are no mechanical fixations of steel that connect the rail to any concrete or steel element outside the rail structure. There is a long history for all kinds of rail traffic. As I said before, almost 50 years of applications throughout the world. I will come back to that later. And most of these applications are based on custom designs. You may imagine rail profiles vary all over the world, but also constructions of channels, pavements, requirements on vibration isolation, they differ per project and per place. So we are familiar with custom design. Maximum integration to structures due to the small construction heights, and accessible by other traffic, a requirement for level crossings. That was about the system. Now a few slides that show you how to build the system, the installation. Basically, the installation is divided in 3 phases. The first phase is the preparation of the rail and the channel. As you know, fresh concrete has a surface layer which is not so strong, and concrete channels therefore need to be cleaned before embedded rail can be installed. Same time, rust must be removed from the rail to a certain extent, and then both surfaces, channel and rail, are covered by a primer to make the rail and the channel suitable for further steps. If necessary, a resilient strip made of track-glass material is glued on the bottom of the channel to control the vertical elasticity and therefore vibration properties. After doing the first step, the preparation phase, the second phase is installation of the rail in the channel, and followed by the alignment. Basically, there are 2 ways of aligning. The first and most common method is by using shims and wedges. Shims for the vertical alignments, as you can see in the left-hand top picture, and shims and wedges for the horizontal alignment. Both rails are usually aligned after each other. One rail is leading, the second one is positioned relative to the first one by controlling the gauge and the height. The other one is the so-called top-down alignment method, for which you need portals. Portals are shown in the bottom right picture. In this case, the rail head is grabbed by clamps in the portal, and the portal itself is aligned in vertical and horizontal direction. It is a good system for higher accuracy, but basically we have achieved quite similar levels for both cases. Drawback of the portal system is that you cannot use a trolley to measure your temporary track alignment before pouring cork-rust. The last phase of installation of embedded rail is creating the fixation itself by pouring cork-rust material. Before doing so, you of course need to seal off the open gaps at beginning or end, or where you have cable connections and drainage points. We do that by means of synthetic material, foam, and seals. As you can see, you also take care of the filling elements, in this case tubes. And when everything is fixed and the alignment is okay, a primer, a bonding primer, is applied on the surfaces of channel and rail. Usually that's a spray type of primering. When pouring cork-rust, you have to take care of the right pouring direction, as indicated in the third picture in the bottom. And after the correct levels have been achieved, you let cork-rust cure for a couple of hours. In the table, you see the general recommended curing time after pouring. In a lot of cases, we perform this pouring procedure in a tent, in which the temperature is a little bit elevated or controlled, so that curing times can be reduced to approximately 3 hours. And then after the curing, the track is open for operational use. Where is embedded rail applied? Well, there is a large variety of structures where embedded rail is applied. This is a brief overview, 8 different locations, type of structures. A brief summary, level crossings, more detail to be presented in about 10 minutes. Is a good and very common application. Why it is so easy to install? What you see is the embedded rail system is in a channel, and you can replace the rail in the channel while keeping the road, for instance, open for traffic. So road traffic and rail traffic can separately be allowed to the track. Waterproof is a very important feature in level crossings because in a lot of countries, salt is used to de-ice the road surfaces, and therefore waterproof rail fastening systems will prevail over non-waterproof ones. That feature of corrosion-free will increase the lifespan, and there are rail level crossings reported with a surface life of almost 50 years. The dominant factor in the rail surface life is the wear of the rail. In, for instance, tight curves where the rail wears out faster, usually the worn rail is the reason to replace embedded rail, not that much the embedded rail system itself. Another quite significant application of embedded rail is on bridges. Unfortunately, today, time is too short to pay attention to bridges, but there are many examples of this, and they are that interesting for embedded rail is that interesting for bridges because it creates a strong reduction of the weight, and it can also enlarge the lifetime of the bridge because it has a load spreading feature. On top of that, silent bridge technology, so making steel bridges more silent, is a concept in which embedded rail is an essential part of this. And if you'd like to know more about this, I kindly invite you to see our video on our YouTube channel. When you get this presentation, you just click the video button on this presentation. It's a really interesting video. In-street is something more than a level crossing because in-street application makes more means that more traffic is on the track, not only in cross direction but also in the same direction as the rail traffic travels. Important in this case is usually noise and vibration control, because the in-street is usually located in the inner cities of and residential areas. Most of these tram systems make use of direct current systems, and there are usually quite a lot of cable and duct infrastructure located in the ground. So stray current prevention and insulation is a key point in designing in-street embedded rail systems. Sorry, that was the wrong button. Well, for a green track, embedded rail is also suitable, even what you can see here in switch and crossing areas. The only thing you need is a nice channel, which can be the case like this in concrete, but also steel, coated steel options are available. Embedded rail in tunnels offers another benefit, the accessibility to road traffic in case of emergencies, but also reduction of construction height. Another interesting application of the embedded rail, depot areas. As you can see here, a nice and smooth surface where vehicles, but also equipment can access the area because it's flat and very accessible. And not only in the outer part of a depot, but also inside in workshops and in special work pits where vehicles are maintained. Embedded rail can help to support the track under the vehicle under maintenance conditions. Another application is in stations, where noise and vibration is usually also a point of concern. More resilient systems in stations do help to reduce noise and vibration hindrance. Flat surface is a nice thing when it comes to aesthetics. Very good to clean and to conserve easier than, for instance, ballasted track or discrete fastenings, and access for in case of emergency situations. Getting away from passenger transport, but going to industrial applications and harbors and ports. Embedded rail is a system with a long-lasting history and a robust system. By choosing the right type of core callasts in combination with low operational speeds of rail traffic, we can allow heavy loads, not only of rail vehicles, but also special road vehicles like these reach stackers and straddle carriers that are typical for harbors. You can imagine if such a special vehicle runs over a rail, that gives an immense load. In this case, industry and port applications are also very common, especially in harbors that are sea harbors or seaports, in which salt air is a threat to the conventional rail fastening systems. Speaking about it, we also provide crane rail systems based on the same principle of core callast embedding. However, we use a specific type of core callast for this, and we market this under the name crane rail systems. For the rest, all features, advantages do apply for the crane rail system as if for the embedded rail system. The embedded rail system is almost 50 years old now and applied in total in more than 100,500 kilometers worldwide in a number of metro, light rail, tram and heavy rail applications. Why just or only 1,500? Most situations in which we apply embedded rail are specific situations due to noise and vibration issues, building restrictions, building height restrictions, or electrical insulation or workshops. Well, embedded rail offers the possibility to customize to a high extent, and therefore maybe the total number of kilometers is not that much, but the places where they have been applied is quite large. One of the field of applications of embedded rail is the level crossing system. Mark already gave you the example of a recent development in level crossing systems, which is the LCS 350, the level crossing which makes use of a concrete slab with a thickness of 315 millimeters. There is the clarification where the number comes from. Earlier this year, the LCS 350 system was installed in New Haven, and it had a manufacturing in Cornwall, so it is a British slab in a British project with some Dutch technology from Nederland. We are very proud of this. It was installed in a relatively short track possession time. The design was economically competitive, and because of the unbeatable stray current protection, it was selected. It has good maintenance performance outlook and track availability during the life cycle. On top of that, the client was charmed by the striking aesthetics because it has a nice surface. I will show you later the possibilities of surface treatments and imprints on the surface as well. It's a little bit hard to see this, these pictures. Last but not least, it has a certain strength which allows heavy road traffic to pass this level crossing. The technical details of the level crossing slab LCS 350 are based on design specifications that originate both from road and rail traffic. First the rail traffic, of course, is based on the UIC load categories D4 and E5, which are the heaviest in their class, based on freight traffic load axle loads up to 26 tons. In the design codes, the Euro Code 1 and 2, attention is paid to the actions on structures, in this case the road traffic. And you can imagine that road traffic is the most adverse situation when a road vehicle is located in the corner of a slab. Well, those situations have all been considered and reinforcement has been adjusted in accordance to this. That has been done according to the Euro Code number 2, applicable to the design of concrete structures, taking not only road loads, but also temperature forces, temperature gradients, support conditions, etc. into consideration. Here in the typical cross-section, you see some main dimensions. Slab is 2.4 meters wide on top, and this is suitable for normal gauge tracks. The track is slightly wider at the bottom to create more support and also to allow surfacing that connects to the level crossing slabs in a better way, for instance, asphalt or stone pavement. The other thing that you see in this drawing are hooks that are suitable for transport. The hooks are located in the channel. That means that there is nothing visible after transport because the hooks are covered by the embedded rail system. There are some additional hooks necessary or used during the manufacturing of the slabs that are located on the bottom and on one side of it. These slabs are usually 3 or 4 meters in length and can be extended if necessary upon demand. Well, the characteristics of the level crossing slab, designed for 30 tons axle road traffic and 25 tons axle rail traffic. Concrete class C45-55 according to the European classification for strength. And special attention is paid to the skid resistance of the surface. In this case, there is a diamond shape imprint applied, but there are a number of different imprints possible. Apart from that, other options that are well relevant in certain projects are available. One of that is the flangeway entry to the slab. Usually the first and the last slab of a level crossing have these flangeway flares to allow the rail not to hit the slab, but to be, let's say, guided into the groove. Another feature is the slab protection plates in case of items hanging on the trains, like elements which are hanging on freight wagons. This protection plate helps to let the element be thrown over the slab instead of hitting the slab. Another feature is steel channels that help protect the corners of the slab on the top from impacts from road surface or from damage from road vehicles. But I said road surface treatments and types of imprints are available. Well, since not all track is in straight, there are tapered and curved solutions possible to install these slabs in curves as well. Roughly 100 meter is the minimum curve length for prefabricated slabs. Below 100 meter, we may think of designing something specific or to install the slab in situ with in situ cast concrete. And engineered designs do exist for higher axle loads, both for rail and for road. You have to think of thicker slabs or densely reinforced slabs to withstand the forces of higher axle loads. But that's an option. The standard LCS 350 is designed for the aforementioned axle loads for road and rail traffic. I think I went, yeah. This is by accident a copy of a previous slide. I'm sorry for this. That makes it a bit confusing. Let me go on to embedded rail custom designing. Here on the right hand side you see a typical cross section of a British rail type embedded in a standard level crossing channel cross section, in which you see a steel profile, corner profile, item number 9, to protect impacts from road vehicles, and the groove width necessary for a smooth passage of the wheel flange, both in width and in depth. On the other hand, where the cork level is a bit higher, we have to allow some water flow, but also prevent too much contact with the rubber tires of vehicles. On the other hand, that part of corklast is necessary over there to have a stable position of the railhead and guarantee lateral track stability. When we go deeper down, we see filling elements with tubes and the contours of elements to position the rail during installation, wedges and shims under the rail foot. And deeper at the bottom of the rail, we see the resilient rail strip. This strip is responsible for the vertical elasticity of the track, which is a key parameter in the design. Well, in order to determine the track stiffness or the fastening stiffness, the vertical stiffness, so to say, we carry out stiffness tests prescribed in the European standard for rail fastenings, and our, let's say, design objective is always to find a system that shows the same rail deflection in the level crossing as in the adjoining or the neighboring ballasted track. Well, we have the ability to change type of corklast material as well as type and thickness of rail strip to balance these two. That is a very important issue, because the same stiffness creating the same deflection prevents transition effects like impact loads in the transition. Not only, the only item elastic in the rail fastening, in the level crossing, is the rail fastening system, because the level crossing slab, the concrete slab itself, is supported by a stabilized, or in fact very stabilized, subgrade. So that's good to understand. Track stiffness in this case in a level crossing is only provided by the rail fastening system. In the adjoining ballasted track, there are more components. It's the sleeper with the rail pad. It is ballast layer and probably also some elasticity from the substructure under the ballasted track. So you see, we have to match both stiffnesses in embedded rail. What is important in level crossings is, of course, that the neighboring ballasted track is well maintained. Ballast has to be in good shape and also in the right position to control track geometry. Preventing voids under the sleepers, the so-called hanging sleepers, are crucial to prevent further damage and further degradation, not only of the ballast part, but also of the level crossing itself. Some railway companies do recommend to start a level crossing directly after installation with a kind of extra height, an overheight, to compensate for future ballast settlement. So a few millimeters overheight will level out in the first months of operation to come to a leveled position of the ballast track compared to the level crossing. And many rail authorities also prescribe the use of stabilizing measures in the adjoining ballasted track, like wire sleepers, geogrids to stabilize the subsoil, or special layers either made of compacted material, bound material, or even prefabricated elements from steel or concrete. The vertical stiffness is important to prevent impacts. The longitudinal stiffness is important since performance of embedded rail, an adhesive gluing, so to say, of a rail to a solid concrete element, is something different and really different than the conventional fastening system by means of rail clips. First of all, at the moment of installation and pouring core-cast material to fix the rail in the concrete level crossing slab, we can follow two philosophies. First of all is to consider it as already long welded, and then we have to be careful. We must install the rail around neutral rail temperature, or we do it differently. We separate the continuous track from the level crossing. We first install the rail over there, and then later connect it to embed to the continuous welded rail at or around neutral temperature, or adopt a stressing method. That is to say, we do not stress embedded rail during installation. We do connect the embedded rail to continuous welded rail by means of either neutral temperature or stressing the continuous welded rail when making the closing joint. As I said, the longitudinal behavior of embedded rail is incomparable to what rail clips do. Rail clips allow the rail to slip beyond a certain force, the so-called rail restraint. Embedded rail will never slip in the adhesive material. No, instead, we must be sure that differential displacements between the rail and channel will never be surpassed. The benefit of this different behavior is that in case of a rail break, the gaps remain very small. Where a normal opening at low temperatures can amount to 10-20 millimeters, the gaps in embedded rail will remain very small, 2-3 millimeters maximum, which gives opportunities to keep the track in surface under speed restriction. But it also gives an opportunity to consider embedded rail as an anchoring point for continuous welded rail. For instance, where you have to separate continuous welded rail from jointed track, for instance. As I said, embedded rail is limited in its maximum longitudinal movement. Differential displacement of 15 millimeters is maximum, and from that moment on, it could happen that the rail starts to separate from the channel and core-cast starts to show the first signs of damage. In order to demonstrate that, you see a picture of a typical test in which the rail is pushed through the embedded rail material through core-cast in a channel. These tests give you not only when it starts to damage, but also the displacement force ratio, the so-called longitudinal stiffness, which is a key parameter in case of bridge design. It determines whether your bridge is long enough to allow a continuous welded rail or must be separated by means of expansion joints and dilatations. That's all I wanted to say about the technical features of embedded rail in combination with a level crossing slab. Some features of the installation method of level crossings. First of all, in a few pictures, you see the excavation of the opening where the level crossings must be installed, compaction of the level crossing area to the required stiffness and supporting stiffness. I'm not sure if you are familiar with the bedding modulus, but the value of EV to at least 100 megapascals is a requirement to guarantee a long service life and a long stable position of the slab. On top of that compacted soil, we apply a level of approximately 10 millimeters fine leveled sand. Here you see how workers do that by means of a very wide ruler. And then when everything is checked and approved, slabs are placed on that sand bed. That's part one. Slabs are closely placed to each other with a gap that must be closed by means of a joint sealing material, which you see in picture number 6, sorry, with also with primed surfaces to guarantee adherence. Once that is done, we can do the next step, the installation of the rail and cork-last embedding, the steps that I introduced to you about 20 minutes ago. And after the installation of this, the rails are usually connected to the baluster track. But usually not before attention is paid to some side elements like drainage, as you can see this number 8 picture. Drainage to collect water from the level crossing and to prevent that the water penetrates in the ballast, and there, especially there in the transition zone, creates excessive problems with settlements or pollution. It's a good idea to have an eye for that and to pay attention to conservation of the transition area in baluster track as well. The traditional methods of installing LCS 350 level crossing slabs is to use sand bed. However, there is an alternative method if the procedure with sand is a little bit complicated or difficult to establish. This method with injection grouts is something which is suitable for more problematic soil conditions, because the grouts gives an extra supporting layer under the slab, and that grout is contained in pockets which is created by means of foam, which are first installed on the ground. Then the level crossing slab is placed onto it. Next, the level crossing slab is lifted by means of jacks to what you can see in the picture on the right, to the correct vertical position, and then the space under the slab is injected by means of liquid grout through holes in the slab. And then after curing, usually it's a fast curing grout, so within a couple of let's say 1 hour, the slab is the injection grout is settled, and jacks can be removed and moved on to the next slab. It's an alternative installation method for those cases where subsoil conditions are not so ideal. Well, I would like to finalize with to finish my presentation with some examples. On the left, you see examples of a number of level crossing slabs in an area in Maastricht in the Netherlands, used by freight road traffic and freight trains. On the right-hand side is more in an urban area where buses cross the level crossing slabs. In Bergen, Norway, but also in industrial areas like in the harbor of Fredericia, Denmark, where it's installed in a container terminal area. Here you can see that some extra provisions are applied by means of steel protections on the concrete wall, as well as rough imprints. Well, A brief summary of references. Level crossing slabs with embedded rail based on Corculast are up to date, installed in about 1,000 level crossings for various applications, light rail, tram and heavy rail, and industrial and ports. Usually those applications are handed in by private companies. Most European railway companies do have some applications of Corculast embedded rail level crossing slabs. It is the default system in the Netherlands railways. We are very glad about that. But also German railways, French railways, etc. make use of Corculast level crossing slab systems. If you would like to see more, you can look at one of these installation or rail replacement videos. The first one is a link to the Moordite Bridge, the one that I would recommend to see if you are more interested in bridge design with embedded rail. Very interesting is Ruislip depot installed in 2018 for London Underground. There are also some technical videos about building information models, BIM in short, that show how we design embedded rail systems and level crossing systems with embedded rail. And the last interesting video is a level crossing replacement in France. Well, that brings me to the end of this presentation, and I would like to thank you also on behalf of my colleague Mark for your kind interest. And this opens the floor for your questions and my answers.
Ladies and gents, if anybody's got a question that they don't wish to speak up, please feel free to use the chat function, and I can read them out if you want to be recorded. But otherwise, please ask away.
Amy, Mark, it's Les Fox here. Hi. Could I just ask a question about depot installations? I've had a bit of experience with specifying and designing slab track in depots, particularly for fueling facilities, fueling aprons, and from experience, the slab track systems we've used previously, we have come across issues where the rubber boots that are part of the system have deteriorated really quickly because of the amount of hydrocarbon spillage on those installations. I was just wondering if you've had the Edelon Cedra system installed on a fueling road or a fuel offload facility where you might get similar issues.
Mark, you have examples?
I'm just trying to think of some actually. Off the top of my head, Les, I'm not 100% sure. However, if you would like to send me an email with the chemicals used, then I can trace it through the company to see if we have done something similar and what the results were in that installation.
Sure, thanks. Yep. I did just have one more question as well, if I may, and then I'll shut up. You mentioned about recycled materials and the green credentials. Is it the Corculast that you use recycled materials in?
No. In Corculast, we do not recycle materials. What we do with Corculast, Corculast can be, after use, can be recycled, but for other applications, for lower value applications.
Oh, I see. Right. Okay. That's it for me. Thank you very much.
So, I mean, it looks like you did a good job.
I've got a question, if you can hear me.
Yes.
Yeah, brilliant. My connection has been a bit poor. My name's Pete Verriart.
Pete, we've lost you.
Your connection.
I don't know if you want to try typing in your question, Pete. Not any easier? While Pete tries to get connection, has anyone else got a question?
I think it's also good to mention at this time that for people who are busy with or involved with Network Rail, the embedded rail system has been approved on the Network Rail tracks since it was before it was called Network Rail. I think it was a rail track approval. And the LCS 350 level crossing, we've had a temporary approval for 4 level crossings, and the temporary approval converts to a permanent approval in the next 4 to 5 months.
Some additional information to Les' question. We are permanently developing improvements of core glass material. One of the research projects that we are on now is bio-based core glass materials, which are no longer making use of resources that come from industry or from oil industry, but origin from natural resources. It's not so easy, but we are working with universities and test institutes to these bio-based core glass materials. We have already achieved some results, probably suitable for light rail applications. But we keep you posted via our website when new range of green types of core glass will see the light and be available for projects.
Okay, thanks.
Jens, I have a question from Dave Bannister from a maintenance perspective. Is it approved for use on bridges, for example, to replace longitudinal timber bridges?
Yes, sure. Every bridge is a different bridge, I must say. We did a lot of bridge replacements where cross timber sleepers were replaced by deck plates, and long timber sleeper were replaced by artificial steel channels placed on top of new timber sleepers, for instance. That depends a lot on how the timber sleepers are connected. If I understand Mr. Bannister's question correctly, long bridges, we have to see whether we need, as I said before, expansion joints to compensate, to allow bridge expansion and rail expansion. Sorry, I'm reading the chat as well. The lifetime expectancy. The lifetime expectancy is so far wear of the rail, and that depends a lot on the intensity, the tonnage on rails, and the curvature of the rail. So normally, a straight track on bridges, rails burn out in, let's say, between 20 and 30 years.
Part of our company, as we discussed earlier, we have competence centers. And as I mentioned earlier, our engineering competence center is in Madrid, but we also have a bridge competence center, which is situated in Munich. And it's an application which for our company is a serious application. It's something that we've been doing quite a while. In fact, the last one that I was involved in was in Zambia for a 1.6 kilometer bridge over the Zambezi, which was done with embedded rail. Okay, next question.
Next question. The drainage solution, question asked by Mr. Hayes. The drainage solution that I showed in the presentation was a one making use of a collecting element. Here you see it, picture number 8, which collects the water that's running from the surface towards the slab baluster track. This is one of the solutions, but it's typically designed for level crossings. In case of in-street running, there are also possibilities to drain, for instance, groove rail by means of drainage elements in the concrete slab. Small boxes and an opening in the groove of a groove rail, or a small opening in the wall of a channel for a vignole rail. There is a lot to share with you in more detail, Mr. Hayes, if you like. Also dimensions and fixing method, either on slabs, in slabs, or whatsoever.
Hi, Amy. Mark, sorry I typed my question rather than speaking, but I'll speak now. Yeah, the slab that I'm thinking of is the one that I've been dealing with, Marple, which is like 60 meters long along the track, 150 meter radius, which is probably the one that Pete's asking about as well. I just wondered if there was any way that you could have a drainage solution within that slab rather than just at the end, but I think you've kind of answered the question there.
Sure, yes.
We would like a bit more detail on that, I think. Les, am I right in saying that our slab at Peel Ports will be on a longitudinal gradient, won't it?
It will, yes. A very flat longitudinal gradient, but to match the highway crossfall, basically.
Yeah. Oh yeah, thank you for that, Amy. I think you've answered that question there.
Okay. Welcome.
If there's any more detail, I would be interested in seeing it, just in case we get asked a question about highway drainage. I've asked another one there as well about surface treatment and skid resistance and whether there are different solutions.
Oh yes, there are. There are solutions, especially for the LCS 350 level crossing slabs. There is a pattern, in this case, diamonds shaped pattern. But there are also brush possibilities to make a brush stroke pattern, or to what is quite common in the Netherlands, to work with granite split. So the top layer is of a more resistant and less wear sensitive material that offers good contact, good grip of rubber tires. Specifications, however, differ per country. So and so does the test method. So we would like to see which specifications apply and which test method applies to validate and to choose the right type of surface treatment in your case.
Okay, thank you.
Welcome.
I think before you get on to Peter's question, sorry, did I miss the answer on Dave Bannister's question about expected rail life and how do we replace the rail when the life is expired?
We talked about rail life, but I don't think we touched on replacement.
That's correct, Lynn. Mark, can you address this?
Absolutely. It's quite a simple procedure. Basically, when your track has expired in life, it means that your rail has expired. So you need to replace the rail. Normally in sections over the length of a stretch of rail, so past 18 meters, we will have a weld pockets. And these weld pockets will be areas where you can cut out the corkolast, cut the rail on the two sections, and then with a rotary knife, it runs along the side of the channel on both edges to break the seal between the corkolast and the concrete wall. And once the seal is broken, an RRV vehicle can come along and you can then pick the rail from one end. You hoist it about a meter in the air, and then you go along the 18-meter section, replacing it that way by putting wooden blocks underneath the rail. Because we found that if you try to pull the rail completely out, you could damage the concrete, which would be unfortunate. So it's better to do in sections, and it pops out. And normally a majority of the corkolast will come out with it. And in this instance, if there is any core class debris left in the channel, if this is not able to be easily cleaned away, then so long as it's only surface amounts of core class, we can pour core class, new fresh core class straight over the top.
If you would like to see the method of rail replacement, I kindly recommend you to see the Moerdijk Bridge video, the first in this overview of available videos. Although it's in a steel channel on a steel bridge, it shows you the principle as well as the details relevant for rail replacement.
Yeah, that's good. Thank you. Yeah, I'll have a look at that one. That's what I was thinking of, to be honest, on a bridge. So yeah, I'll have a look at that one later. Thank you.
And touching back onto Pete's question after his connection problems, he's asking about tight radius curves, about circa 150 metres. What method of rail alignment would be most appropriate during installation?
In this case, usually the rails are pre-bent. That means that the rails do not have to have too much force to bring them in the right position, because they are bent according to the applicable radius. That means that both methods can be applied. The most common is the bottom-up method by shims and wedges, usually apply in curves, more wedges than in straights, to prevent stresses on too high stresses on the wedges. Of course, it must be high temperatures can influence the positioning of the rails. So it's better to do the track alignment before pouring Corcolast in a condition in which the temperature does not change too much. Otherwise, you can lose your rail position. That's typical for tight curves. And the second thing is work with pre-bent rails, and that basically whether you use top-down or bottom-up does not matter too much.
In these cases in the UK, however, it's we're opting for a bottom-up installation. The involvement of portals, when you're using portals, the portals have to be adjusted, and they also have to be checked after every use to ensure that they're still within the scope. So yeah, and if we're looking or referring to peel port, then in this instance, I'm not sure if the rails will be supplied pre-curved, but it definitely will be a bottom-up installation.
Yeah. And on top of that, I would like to say that using a trolley to check the rail alignment is easier in case of bottom-up alignment than when using portals.
I think we will specify that the rails are pre-curved, Mark, on peel ports. I think that's essential. Yeah.
Yeah, fortunate. We also have to understand here. In our presentation, we discussed that we have a 150-meter radius on the slabs. However, on light rail, heritage rail, we have gone down much further. We've installed at the beginning of this year, we were installed on the Isle of Man slabs with embedded rail down to 24-meter radiuses.
Those were designs.
Sorry?
Those were custom designs, of course.
Yes. Yes.
Tapered or with curved channels.
Correct.
Yeah.
Could I ask on a long slab like the one at Peel Ports that we keep labouring over, where you're going to have to join 60-foot lengths of rail together, have you got any preference over the type of weld that we'd use, thermit or flash butt? Does it make any difference?
No, it makes no difference. From experience, the flash blood is faster and better. Yeah, flash blood is that yeah, that's possible in track as well with a machine. Yeah.
Okay, thank you.
Yeah, no difference.
Oh, looks like we've gone through the questions.
Yeah, is that everyone?
I had one more, Lynn, sorry.
No.
I noticed on the presentation, I think you said that it was generally designed for 30-ton axle load for highways loading. Is that correct? I presume in the UK where we have 40-ton HGV axle load, that slabs are still fine.
Yeah, the standard LCS 350 slabs are designed according to the Eurocode with a load model for road traffic of 30 tons. But we have a version which is suitable for higher road vehicle axle loads. And that is in two items it differs. It differs in steel protection of the channels. And it differs in, of course, the reinforcement and the concrete quality of the slab. So the dimensions remain the same, but the strength of the slab is higher.
Unfortunately, we have everything or nothing here. This one slab, the LCS 350, has up to the 30-ton road loads, and then we jump from 30-ton to a maximum of 100-ton. So everything after 30 and under 100 is our LCS 350 CT version, which is for the higher road axles.
Okay, thank you.
Yeah.
All questions, guys?
Yeah, there's plenty of detailed documentation about products and systems, so Mark can perfectly answer your detailed questions if you like. Isn't it, Mark?
Well, absolutely.
Yes. His contact details are on the last slide.
Right, gents, I think that, yeah, it's time for us to say our thanks, and thank you very much for taking the time to prepare the presentation and to deliver it online as well. I know it's not the easiest of formats, but it really is appreciated.
You're much more than welcome.
Yeah, thanks, Mark and Abby. It's excellent. Yeah.
Thanks, Les.
Thank you so much. It was a pleasure to be with you.
Thank you.
And thank you, everyone, for tuning in.
Cheerio, everybody.
Good evening.
Lynn, I stay online to exchange some last details.
Yeah, hold on.
Okay. Yeah, hold on.